Good morning to all of you to the live session. So first I will discuss the question that has been asked from the syllabus. So from the open air oxidation, so we have told in the class that if you put aluminum isopropoxide and arabenzoquinone under this condition you get the dienone. So in the revised mechanism we can show here. So what happened? This hydride is actually attack the parabenzoquinone oxygen. So you can see this kind of isomerization is happening, and now you see this hydride is attacking here, and you will get quinol. So what is the product here? You get now dienone. There are some substance here. So that is the most possible mechanism. And another one we discussed that when you put the cyclohexanone to a related substrate, so here hydroxy, so in this case enone is formed, and this is forming via isomerization, double bond isomerized. And one explanation could be that cyclohexanone is less strong, means less hydride acceptor compared to the parabenzoquinone. So what happens here? First the simple oxidation will happen, open air oxidation. So you get the isolated double bond whatever was there in the substrate, and now what will happen? This will go to the enol, so this is the tautomerization to the enol, and now again protonation will happen. So you get the conjugated ketone, that is the enone. Okay, someone asked about acid sensitive group because many reactions we have told that it is not good for the acid sensitive group. So someone asks what are the acid sensitive groups. So silyl protection like OTBS group, OTMS, then acetals, also THP, tetrahydropyran. So what happens if you react dihydropyran with alcohol? You get this protection. This protection. So this also can be deprotected by acid. So if you put PTSA methanol, you will get deprotection. Similarly, base sensitive groups are there. So acetate OCO RO it can be deprotected by potassium carbonate, methanol to ROH. So this you have to keep in mind that acid sensitive group and base sensitive group. Okay, another question was PFC oxidation of anthracene. So in the class we told that if you react anthracene also phenanthrene you get the oxidation. So if you remember the PFC structure, this is O minus and pyridinium ion is there. Now when phenyl reaction type happens with anthracene, the middle ring reacts. So most likely, earlier cases we have told that it reacts to the chromium, but in this case, it attacks to the oxygen. So you get a carbocation here, and your double bond goes to here. So this ring is aromatic. So two benzene rings are there now, and so chromium 6 become chromium 5 now. Now what will happen? This happens the removal of the proton. So you get now here ketone. And you get It's become 4 now. Now this carbocation again reacts with this anion O minus uranium H. So this is anthraquinone. Okay, another question was asked about Baeyer vinegar oxidation, the secondary orbital effect, secondary electronic effect. So that we discuss now. So Rm is the migrating group that will migrate, and this you know if you give the R acid, then you get the A star. Now first what happens, this attacks here carbonyl and you get this intermediate. And this can be activated by the acid or acid. So now what happens, this is the intermediate, now your the rearrangement will happen. So that we told that this has to be anti-periplanar, this RAM should be anti-periplanar to this. This is same like SN2, that because this is cleaving here, this bond, so this and this should be anti-periplanar. So we can draw here and what we are doing, we are looking at this bond, this oxygen carbon bond we are looking, okay. So this carbon is here and two lone pair. Now, so if you see this, your this RM is antipreparator to this O bond, because this Rm goes to this oxygen and then this bond click. So this is the secondary electronic effect. And also your Rm should be antipreparator to one of the lone pair of the oxygen. So that also, so this is oxygen. So this is oxygen. Oxygen and behind is carbon. So this oxygen carbon bond we are looking. So oxygen has one hydrogen and two lone pair, and this carbon has R, Rm and this one. This O. So this has been drawn like this. And now this is very important. Your Rm should be antipreparator to this O bond, and also it is antipreparator to one of the lone pairs. So this is important in the Baeyer-Villiger oxidation. Okay, so one student asked Ahmed Sheikh, this reagent is analogous to pyridinium chlorochromate. What is the effect of fluorine? So this we have already discussed in the class that HF is less acidic compared to HCl. So PFC is less acidic compared to the PCC. So some reactions where PCC cannot work because of the acid sensitive, PFC will work, and these reactions are special of PFC only. So another reaction, that is Birch reduction, and someone asked about the mechanism of the reduction of the heterocycles. So this we have told in the class, I think. If you have a electron withdrawing group on the benzene, then sodium, liquid ammonia, then you get dot minus, and this, then this minus, this minus goes to the para position, and then because this is the maximum, they should stay apart. So that's why this radical anion stay apart, and now your protonation will happen. So suppose if you use ROH, now your protonation will happen at the para position. So that's called the para protonation. And now again another sodium will come. You get the anion here. And now you can use an alkyl halide. Suppose if you use iodomethane, your alkylation will happen. So this selectively happens the carbon where the EWG group is attached. So same mechanism happens with spiral. So what happens if you put sodium liquid ammonia? See, this is the ketone position at the 2 position. So similar way, the one single electron attack here, and you get a anion here and radical here. First the radical at the carbon where the ketone group is attached, Now, as I told earlier that this will stay apart, so this also, this negative charge now will go here so that they are staying apart. So this is the resonating structure. So now we have negative charge here, radical. Now your protonation, so if you see this reaction is in the alcohol solvent, so alcohol will come. Now again another sodium. So similar like this negative charge at last formed at the carbon atom where electron withdrawing group is there. Now if you put the iodomethane, so this alkylation happens at the two position where the ketone group is present. Now if your ketone group has the three position, and I already shown this example, so here I am showing the detailed mechanism. So again this radical will form first at the carbon atom where the carbonyl group is present, and you get a negative charge here. And here this negative charge cannot stay apart because you see there is no double bond. So what will happen, this will be protonated here, and in this case in the example whatever I taught in the class that TH was used. So here the NH3 only will donate with protonate this negative charge, so you get hydrogen here, hydrogen, and dot here, R2. So now again negative charge will form here. So in this case you get this product. You can see 2,3-dihydropyrrolate, 2,3-dihydropyrrole, and your methyl is at the position where it is connected at the three position where the ketone group is present. So this is important. If your ketone group has the two position, then alkylation will happen at the two position, and if your ketone group has the three position, then your alkylation also will happen at the three position. Okay, another question was asked from the Swan oxidation. So for this substrate, this substrate, we have told that Swan oxidation cases, if you use the strong base, then you don't find the isomerization, but if you use triethylamine, then you get the isomerization. So this is the standard condition for Swan CH2Cl2. So what happens? First, this dialdehyde will form, but in triethylamine, what will happen? This hydrogen will be abstracted by triethylamine. So triethylamine can go there and abstract the proton. And so this is like minus H plus H plus. So what will happen in the double bond isomerize? So you get this product. So you get the alpha beta unsaturated aldehyde. So this is stable and already this is double bond, so the stereo center is lost. Now if you use strong means bulky base, so that's what it has been found. Like same condition here. Here now if you use the diisopropyl ethylamine, so this is called unique base. So here you get the normal product. So no isomerization of the double bond. So in this case, because this is of the bulkiness of the substituent here with the nitrogen isopropyl, this hydrogen, whatever is here, this hydrogen cannot be abstracted by the unique base. So you get the normal product. So this is the isomerized product. Okay. Another question was asked the borylation. IPC2B allyl. So this, if you draw the groups, so you get the allylation and stereoselectively you get I think above 95% E. So this is called Brown allylation. So the question was asked how the selectivity is happening. So we can draw the transition state. So it goes via chair transition state. So this is the aldehyde, and now you have the two isopenocamphenyl group. Methyl group. So these are the methyl group. So what happens here? The allyl group, see this allyl group is away from these groups. So allyl group oriented, and this aldehyde also approaches. So here this interaction. So this is the six-membered, you can see transition state, and this aldehyde is activated by the boron. So no external Lewis acid is required. So here aldehyde also approaches on opposite side of the methyl groups. And this methyl takes pseudo-equatorial position. Now we can put these groups R group isopenocamphenyl. Now if you see that this is in zigzag, so if you draw this molecule, then we can draw like this. Because your OH is down, so these are the normal zigzag we are drawing. So this is now down OBR2, and this means if you give a C2 rotation, if you bring methyl this side, left side, then it becomes like this. And after H2 to H minus, you will get the alcohol. So this means if you use the plus IPC2B allied, then you will get the other enantiomer. That is the which will be downside. Okay, so one question asked from Sobik that can 1,4 addition take place at the last step when you are adding methyl iodide? Yes, that is also possible. If you generate the negative charge, that means you can do the Michael type addition also. And Hani Sharma asks, explain the mechanism of quinolines on Barch reaction in presence as well as absence of proton salts. So quinoline case also can discuss. I think one ring will be I need more page. So what will happen here? So it will form the dot minus there. In RH. So you get this, I think, after proton source. Any more questions? Okay, someone asked about this pinnacle rearrangement. So just I want to show one example. Because this is not really I discuss in the class. So one is this cyclohexane diol system that it is very interesting. So if you have a trans diol, so this is of course diaxial, this is less stable, so it will go to the diequatorial. So here also two hydroxy groups are trans, so this is more stable. So what happens if you put acid now? This these both are almost symmetric here. So if you put the acid here, this will be protonated. And now this anti-periplanar orientation you have to see. So this bond is anti-periplanar to this bond. Similarly, if this also getting protonated, then this bond is anti-periplanar to this bit. So what will happen? Because these carbocations are not so stable, so the attack will take place in anti-periplanar orientation. So what happens? You get here cyclopentane product. So you will get, because this will be going to the carbonyl and this bond attacks to this. So you get the cyclopentane carbaldehyde. Now if you have the cis one, so in this case you can see that these two hydroxy groups are different. One is axial equatorial. So this one is antiprior to this hydrogen and this OH is antiprior to this one. So what will happen if you put H plus here? You get mixture of products. So if this getting liberated as water, then this bond migrates. So you get of course here this one carbaldehyde. But if this one liberates, then this hydrogen goes. So what happens? This one becomes like this hydride goes here and then this liberate. So you get cyclohexanone. So you get mixture of products when cis diol is used. So regarding this assignment questions, our TA will answer your questions. So that I am not going to discuss here. If you have any issue regarding assignment, and the TAs will solve this. And Harish asked that how to remember reagent works and function. So this you have to understand by mechanism and their where the which is the nucleophile, electrophile. That way you have to remember. If you understand the mechanism of the reaction, then it will be nice to remember. Gautam asking Clemenson reduction is possible in neutrality or not? No, Clemenson reduction is in the acidic condition and Wolff-Kishner reduction in the basic condition. That you have to remember. So Clemenson condition HCl is used, so you cannot keep acid sensitive protecting group during Clemenson reduction. So Vic, is there any cis or trans selectivity for oxidative addition? Please tell which kind of reaction, which reaction you are telling. Okay, that we did not discuss, but just I want to say that if you have already a stereo center like bromonium ion, you know this bromination or epoxide opening case. So in this case, if there is already a stereo center, then the trans product only will get like the epoxide opening by water or other nucleophile, then you can get the trans product, and for bromination also you get trans product. Now, when the osmolation case like dihydroxylation get, you get the cis selectivity because the double bond is acting with the osmium and with the oxygen of the osmium, so you get the syn addition. But when it is stepwise like bromination, epoxide opening, you get the trans addition. Okay, this we'll discuss in the next one, that Madan Kumar, the carbamate to enemy by SMEH. Okay, because we will have another two live sessions, so we'll discuss in that live session. So Honey is asking the explain the migration in 2-fluorocyclohexanone, which alignment in axial position when in biological oxidation. I think this already explained in the class. Okay, Sobik again is asking in coupling reactions with transition metal, is there any selectivity when the substrate is added to the metal side? So these things you have to remember, like when you add some vinyl iodide in the cross coupling reactions, then the stereochemistry of the double bond will retain. So if you have the cis vinyl iodide, then you get the cis substituted olefin, like in Suzuki coupling reaction. So that olefin geometry will retain in the reaction. And for Heck coupling, that you have to remember, for Heck cases you have to have the syn addition and syn elimination. So this selectivity is completely dependent on the mechanism, what is happening there. So in Heck coupling you have to check that the syn addition and the syn elimination will happen. Okay, if there are assignment related answer, if something is issue, then we will solve there. Okay, if the answer is not correct also, then we will give the marks. Okay, if the wrong is from our side, then you will get the marks. Don't worry. Oh, Honey is asking that dipole effect in case of 2-fluorocyclohexane on axially and equilaterally case you cannot understand. So this you have to see that the O bond, that whether that is close to the fluorine, or because fluorine, that CF bond has some dipole. Okay, so that you have to see that the O, whether that group is away from this or not. So then you can understand. Okay. Okay, this Ahmad Sheikh asking cyclohexanon to cyclohexane. So if we will check again, okay, we will check the assignment again. If there is an issue, we will let you know. Yes, I think TAs will give you the solutions of assignment. I think he already is uploading the answers. Yeah, I think he will also give you the mechanism. Okay. So we'll end now and thank you